Let me tell you a bit about IMarEST's Stanley Gray lecture. I don't know how many of you have been to a Stanley Gray lecture before? Not many. So, Stanley Gray. Stanley Gray was the chief mechanical engineer at the Port Directorate of Basra in the 1950s and 60s. And when he died in 1973, he left half of his estate to the Institute. And he left it to create the Stanley Gray Fund. His wish was that the Institute use the money to award via scholarships and other means wherever engineering excellence was recognised. And of course, over time, as the Institute has grown in scope, the scope of the awards has grown to include science and technology as well, marine science and technology. And we started the series of Stanley Gray lectures in 2002. We hold them not just in the UK but around the world. And tonight's speaker, Professor Alex Rogers, he's it used to sit on the screen, but he's the Science Director and Trustee of Nekton and the Nekton Oxford Deep Ocean Research Institute, Professor of Conservation Biology at the Department of Zoology, University of Oxford, Scientific Director of the International Programme on the State of the Ocean and the Scientific Advisor to the Global Ocean Commission. Global Ocean Commission. Professor Alex Rogers is one of the world's preeminent oceanographers, which is, I almost said cartographer because but he's not, he's an oceanographer, preeminent oceanographer. His research is focused on understanding how communities of marine organisms are structured, what human activities impact them, and how resilient they are to those impacts. He's led and participated in 20 major marine expeditions. His marine policy work includes projects for the UN International Seabed Authority, UN Division of Oceans and Law of the Sea, the IUCN, and the G8+5 Global Legislators Organisation for a Balanced Environment, or GLOBE for short. We're absolutely delighted that Nekton is a new marine partner for the Institute, and we're even more delighted that Professor Alex Rogers is here to give us the talk tonight. Thank you very much.
Okay, thanks. Really apologise for the late start of this talk. As you can imagine, video is always a bit of a nightmare when you're going to talk at another place, so we've run into a few technical issues. But with more to do, I think it's best just for us to kick off. So I'm hoping this short video will introduce the talk.
It's one small step for man, one giant leap for mankind.
Our economies, our livelihoods, and our food all depend on our oceans.
The Great Barrier Reef is dying.
They are literally destroying the reef wholesale.
Systematically devastated our global fisheries through destructive practices.
Government scientists sounded the alarm about coral, and the oceans are in trouble.
Leading us to unprecedented damage to the oceans and the animals living in them.
No one believes 5% of the world's coral could be lost this year.
As much as 8 million tons of plastic waste enters the oceans every year.
We confront an urgent choice.
We are tied to the ocean, and when we go back to the sea, we are going back from whence we came.
Here's the challenge. The deep ocean is the most critical part of our planet, yet it's the least known.
We have better maps of the Moon and Mars than we do of our own seabed. So how can we sustainably manage and protect the ocean unless we know its function, its health, and its value to us?
The big problem we have with understanding the deep ocean is we simply don't understand the distribution of life within it. The fastest way to change that situation is to develop a series of global ocean expeditions from 200 metres down to 2,000 metres, which we call the bathyal zone.
The bathyal zone is home to the greatest diversity of species anywhere in the ocean and contains all the critical indicators of ocean health. It performs an essential role for the planet in absorbing carbon dioxide and regulating climate. But with its wealth of oil, gas and fish, it's the region most vulnerable to human exploitation. It's clear we need a major step change in our understanding of the deep ocean.
Okay, so that kind of introduces some of what people think about the current situation in terms of the ocean. But what is the deep ocean? Well, essentially it's all of the ocean that's deeper than about 200 metres. And when you think that the average depth of the ocean is about 4.2 kilometres, and it reaches a maximum of nearly 11,000 metres at its deepest, so deep you could actually fit Everest in with quite a few hundred metres to spare, you realise just how vast this ecosystem is. It's about 1.3 billion cubic kilometres of water. It is by far the largest ecosystem on Earth, and essentially is home to most of life on Earth. And the way that we actually divide it up is really according to physical conditions, but also the biology in the ocean. So you see this zoning down to 200 metres. That's the euphotic zone where most of the production of food takes place in the ocean. Then we've got the zone from 200 metres to 1,000 metres, the mesopelagic zone where there is some sunlight detectable but insufficient for photosynthesis, and then beyond that the dark ocean, the zone in which there's an absence of sunlight but there is light in terms of bioluminescence and so on. We actually divide up the ocean politically in a very, very different way. So you can see here, essentially we have state territory, which is out to about 3 nautical miles from the coast, essentially the distance over which a cannonball could be fired. Then territorial seas out to 12 nautical miles, and the exclusive economic zone out to 200 nautical miles, where states have a right to exploit the resources around their coasts. And there are currently negotiations going on about extension of that exclusive economic zone in terms of extended continental shelf. Beyond the EEZ we have the high seas, and just to complicate matters, we also have the seabed, which is under a different legal regime to the water lying over it, called the area. So this is a topographic map, or at least as much as we understand in terms of the topography of the ocean. You'll see that there are these large blue areas which are relatively flat, abyssal plain, and then the sea floor is divided up by these seams, which are essentially the mid-ocean ridges. And much of the deep ocean looks something like this. Endless hundreds of miles of mud and sediment. But you'll notice that there's all sorts of bioturbation in this sediment. There are burrows, all sorts of small organisms living there. So actually, although that looks like a relatively barren environment, it does in fact contain a high diversity of species, small animals living in amongst those sand grains. And there's the odd beast like this octopus. If we carry on watching this animal moves menacingly around and then advances on our robot that we have down the deep sea bed here. But not all of it is like that. The deep sea has many what we call hotspot ecosystems, which seem to act as biological foci in the deep sea. So these are things like seamounts. This is the UK zone seamount, the Anton Dorn seamount to the west of Scotland. We also have underwater canyons, deep sea coral reefs carrying down to depths of about 1,500 metres. And all of these places are places where we seem to have much richer concentrations of life. But we don't actually know that much about these ecosystems. And these are data which come from this report, which came from the European Marine Board in 2015. And you'll see here the amounts of these various habitats that have actually been investigated by scientists in the oceans. And you'll see here deep water pelagic, about 1 billion cubic kilometres. We've looked at less than 0.0001% of that ecosystem. At the very best, we know about a third of where hydrothermal vents are. These are these deep sea hot springs in the deep ocean. But for many of these ecosystems, for example the seamounts, as I've mentioned, we've only investigated a tiny fraction of what's actually out there. As a result of that, what we understand about the distribution of life really plummets as we increase in depth and increase in distance from the land. So what you see here are all the records on the Ocean Biogeographic Information System, which is a big database of marine species where they've been sampled and recorded. And what you can see here is that there's a big decrease in records of animals as you move from the surface to 1,000 metres, and then another big dip as you move from about 4,000 or 5,000 metres essentially into the ocean trenches. And here we're talking about literally a handful of records at these depths. We are learning more about the distribution of life in the oceans though, and much of the work has been done with fairly primitive looking equipment like this. This is what's called a spade box corer, and what it does is it takes just a nice neat plug of sediment and brings it up to the surface, and that sediment is sieved, basically using a fancy dustbin and some sieves to actually collect the animals living in that sediment. And we've actually discovered something about the patterns of life in this largest ecosystem on Earth by doing this. And one of the first things is that the biomass and abundance of animals declines as you get deeper. And the obvious reason for this is that essentially the supply of food gets lower and lower the deeper you go. As I said, all of the primary, or most of the primary production in the ocean occurs in the upper 200 metres, and as that material sinks, it's consumed by bacteria and larger organisms, and so the supply decreases with increasing depth, and therefore the biomass and abundance of animals and also the size, depending on the lifestyle of the animals, decreases with depth. However, that is not the pattern we see with diversity or the number of species we see as we increase in depth. Instead, what we see here is a parabolic pattern of species diversity with depth. In other words, the peak in diversity lies somewhere in the middle of what we call the bathyal zone, between about 1,000 and 3,000 metres. So these are some data from off the Rockall Bank. Well, actually the continental slope of the Rockall Trough. The Rockall Bank is over here. This is the Anton Dorn seamount I showed earlier. But these are other data from a much larger review by Mike Rex in the US. And you'll see that for a whole variety of different groups of organisms, from fish to various small invertebrates, we see the same sort of pattern in a number of different areas of the world's ocean. We're not entirely sure why this is, but it is probably related again to food supply. So in shallow water, where there's lots of food, animals can outcompete each other, and as a result there's a depression of diversity. In deeper water there's insufficient food for organisms to really dominate a particular habitat, so we see more cohabitation of species. And then when we get into really deep water, food becomes truly limiting and pushes that diversity down again. We're also starting to assemble larger data sets which are starting to tell us just how different the deep sea is from shallow water. And this is an example of a recent study by Woolley et al., which was published in Nature. And what this shows is that the peak of species diversity in shallower waters, this is still deep sea, 200 to 2,000 metres, is correlated to temperature, whereas in deeper waters it's correlated to the amount of food sinking from the surface. So the patterns of diversity we see globally contrast quite markedly as you change depth. And as I said, this paper was only published last year, so this is a very new finding. The deep sea is important for other reasons, and that is because it provides goods and services for humankind. These include really obvious things like fish as a source of food, but also much less obvious things like nutrient cycling. And there are also cultural benefits from habitats like this as well, in terms of their inspiration and educational value and so on. And indeed, following the 2008 crash, states have really started to look towards the ocean as a way of boosting their economies. And this has been termed blue growth. And you'll see here, this was from a report, I think it was about 5 years old, this one. And essentially it defines the blue economy as all economic activities associated with the ocean, seas and coasts. This includes direct activities such as fishing, but also indirect supporting activities such as building ships and making nets and so on and so forth. And it's estimated that in Europe the blue economy employs about 5.5 million people, with a gross added value in economic terms of about 500 billion euros per annum, about 4 to 5% of gross domestic product. What are the most important activities? Well, surprisingly, I think really, coastal tourism turns out to be one of the really important activities here, but then there are things which you might sort of think of as a top 10 here, things like shipping, oil and gas, fisheries and so on. However, Europe and other states are now looking towards the deep ocean as a way of expanding their blue economies. And this is looking at traditional industries like fishing and energy. Something like 40% of the large oil and gas reserves in the world are actually in deep waters, but also to new areas of activity such as deep sea mining, blue biotechnology, and even, bizarrely enough, tourism. This is a picture from a tourist submarine in Roatan in Honduras, where people actually pay to go and see these blunt-nosed six-gilled sharks eating dead horses, essentially. The really interesting thing about this move into the deep ocean, though, is that this ecosystem operates in a very, very different way to the shallow water ecosystems that we're used to operating in. And this is just one example. This is a single sponge spicule from a deep sea sponge called Monoraphis chuni, found in the East China Sea. And you'll see that single spicule is 3 meters long. And you can actually section these spicules and age them through isotopic means. And it turns out that these animals live for an estimated 11,000 years, a single colony of sponge living in the deep sea bed. If we look at animals like black corals in the deep ocean, you'll notice immediately this coral isn't black, but actually the skeleton is black. That's why they're called black corals. They come in all sorts of wonderful yellows, and oranges and reds and so on. And these animals live for up to 4,200 years or more. And this is only based on a relatively few aging studies. So we're talking about animals which have been around really since the Stone Age in the same place and essentially have lived through all of that time. So you can imagine if these types of organisms are impacted by human activities, they're not going to return very, very quickly. They're very, very slow in terms of growth very slow to reproduce and recolonise areas. And this has been very much the experience of some elements of the deep sea fishing industry, where species like this is the orange ruffy, it's probably one of my favourite species. This is a fish that was targeted first in the Pacific by deep sea trawl fisheries, and it was found relatively quickly that they cannot sustain much in the way of fishing pressure. And the reason for that is quite simple. They live for an extremely long time, more than 150 years. They don't mature until they're 30 or 40 years old. They only reproduce sporadically. And unfortunately, they get together in huge masses to spawn over discrete areas of elevated topography, in other words, seamounts and areas of raised continental slope. And unfortunately, what we've seen is, as shallow water stocks have been exploited and overexploited, we've seen an increase in the depth at which fishing has been taking place historically since the 1950s. And this is just one example of one of these orange ruffy fisheries. This was the Irish orange ruffy fishery to the west of Ireland, and you'll see here how in the early 90s they were getting catches of these animals and realising that they had a marketable catch here. And what happened then was there was a major investment by the Irish government into the deep water fishing industry in Ireland. So the vessels geared up to fish orange ruffy. The catches really ramped up all of a sudden, and then basically they collapsed within 2 to 3 years of that fishery commencing. And what you see there is just an example of essentially an unsustainable fishery. Because of the life history aspects of this particular species, they simply cannot sustain a high level of exploitation. Coupled with that, we've discovered that there is significant environmental damage associated with certain types of this fishing. And the problem is that orange ruffy happen to co-occur with some very fragile deep sea ecosystems, such as these cold water coral reefs. And here you can see a cold water coral reef, and this is actually from a seamount to the south of Tasmania. And this is a seamount that was not fished for orange ruffy and another deep water group called Oreos. This is a seamount in the same area that was fished for orange ruffy and Oreos and so on. And this would have been covered in cold water coral reef prior to the fishery taking place. And you can see that framework has been completely destroyed, and there have been scientific studies done in this area which show a direct correlation between the amount of coral framework and the biomass and diversity of species living on the deep sea bed. So when you see organisms like this is a huge octocoral, corallium. I think it's been fished on the Louisville Ridge. I'm not quite sure. I know it's a New Zealand vessel, this one. That is probably thousands of years old, that coral. You can see there where from a single trawl drag that's simply been pulled off the seabed and is not going to recover. Our first problem with trying to manage these types of activities in the deep ocean is simply understanding where these habitats occur. And these types of ecosystems often live in places like seamounts. And this is a satellite map of seamounts. We can actually map using gravity data and sea level height data and approximate what the shape of the seabed is under the ocean. And by doing this, we can predict where the seamounts are in the ocean. This particular study identified up to 33,500 large seamounts. These are seamounts of an elevation of more than 1,000 metres, and more than 130,000 smaller features if you include those as well. And this turns out to be a significant area covering the deep sea floor. So these ecosystems are not just randomly scattered and the odd one here and there. They are in fact a very common ecosystem in the deep sea. we were very interested in this, and what we actually did back in 2011, I think it was now, was we went to look at one of these areas of seamounts. This is in the southwest Indian Ocean, where there'd been no previous scientific investigations, and we used models to predict where these coral ecosystems might occur on the ridge, and we also wanted to look at the impact of fishing, which we knew was going on there. So this requires some fairly substantial technology, and the RRS James Cook, which is a UK research vessel, and in this case German ROV, the Kiel 6000. And the nice thing that I could stand here and say is that the models certainly seem to identify areas where these corals occurred, and this is video film probably of the first cold water coral systems actually seen in the Indian Ocean on one of these seamounts. This seamount was called Coral Seamount, and interestingly, essentially as a response to pressure coming from the UNGA, the fishing industry in this area voluntarily closed this seamount to fishing because they were getting a high bycatch of corals when they were trawling. There were a lot of other amazing habitats on this seamount, and we're continuing to publish records of new species, new ecosystems. I put this one up, and I could put many up, but this one up because it's a particular favourite of mine. These are Venus basket sponges, and inside every single one of these is a pair of shrimps, a male and a female shrimp, and they basically live, each pair, in one of these sponges, basically produce their eggs, and off the larvae go. So we're not quite sure what the sponge gets out of this, but the shrimps certainly get protection, because if you try and pick up one of these, you find your hands are immediately covered in lots of very sharp glass shards. These sponges are made of silica. Unfortunately, what we also found was evidence of completely unreported fishing going on these seamounts. So this is a seamount called Melville Bank, and what we discovered when we got there were lots and lots of lost lobster pots. Now when you think this seamount is 5 or 6 days away from the nearest land at full speed, literally in the middle of nowhere, and yet it's been found by the fishing industry and very heavily exploited. And this is what they were after. There were a few left. This is basically a rock lobster. It's a Jacer species. We're not quite sure which one. There have been new species found relatively recently in the Indian Ocean where these types of fisheries have taken place nearer to South Africa. And along with the lost lobster pots, we also found other types of lost fishing gear as well. And you can see here one of these lobsters completely caught in a ghost net. That animal is dying. It was just barely moving when we found it. And of course, when that dies, it attracts in other fish. They get caught, and the whole cycle continues. And we had a very hardened ex-North Sea crew on that ROV, and even they were going, let's go in and rescue this animal. And of course, we just couldn't risk getting several £1 million worth of ROV snared in that material. And of course, along with the fishing, there was various other debris tossed overboard from the fishing vessels. This is a fisherman's glove. You can see it's a bit of a mixed message, this slide, because this eel has clearly made it its home. But actually a really shocking story came out of this. Lucy, who's sitting here in the audience, rang me up one day from the Natural History Museum, who were partners on this project, and said, Alex, I'm finding loads of plastic fibres in all of the sediment samples we took on the cruise. And it turned out that essentially what we'd found was that the plastics are being pulled out of the surface of the ocean, probably on sinking phytodetritus or marine snow, all the dead stuff that drops out from the surface of the ocean, and it was ending up in the deep sea. In every single sediment sample we took, and even all over the corals and animals, we found this material. And also Lucy looked at the marine litter, and you can see here the sort of graphic representation of the amounts of litter we found on the seamounts, and this is compared with similar litter studies in the Atlantic, and you'll see most of the litter here is basically fishing related, whereas the litter here seems to be coming from a wider variety of sources, including shipping. And here you can see basically the amounts of pieces of microplastic per 50 mil of sediment, and you can see here these are samples from the North Atlantic and Mediterranean. The samples from the Southwest Indian Ocean had lower concentrations, but essentially it's there wherever we look. It's not just the hard bottom communities which are affected by fishing activities, and although I can't give you details of this because this work is actually in submission at the moment, we have looked at the largest set of samples ever taken in the deep sea in the northwest Atlantic. So this is an area which has been fished for quite some time for a variety of species, and here we've looked at the animals living in the soft sediments on the seabed. And again, what we find is that with fishing, basically the abundance of animals actually seems to increase, but the functional diversity of the whole community seems to decrease. So what we're seeing here is an effect that's quite similar to the type of situation you get under a fish farm, where there's organic enrichment of the sediments, and although you get an increase in biomass of the animals living under the cages, whether they're salmon cages or whatever, the actual functional diversity of that community is reduced. And what that means is there's an impact on ecosystem function. We also discovered that there is a very, very high level of sensitivity to temperature change, which really has significance in terms of thinking about the effects of climate change on these ecosystems. So, moving now from a legacy industry in the deep sea to one which is on the horizon, and that's deep sea mining. And deep sea mining is targeted at a variety of different types of deep sea habitat, or it will be. One of them are deep sea hydrothermal vents. So here are hydrothermal vents we discovered in the Antarctic. This is at a depth of about 2,500 meters, and that water is coming out, or that fluid is coming out at more than 340 degrees C. And the black smoke you can see there are metallic sulfides precipitating from the transparent hydrothermal fluid when it hits cold seawater. So it gives this appearance of black smoke. So all of these structures around here are formed of hydrothermal minerals, and if you look at the structure of these chimneys, this is the type of thing you see. So this is basically a form of copper pyrite, and these chimneys and deposits around these vents have high concentrations of various metals and minerals that are of course of interest to us in commercial terms. At the moment, these machines are wending their way out to Papua New Guinea to perhaps begin the first deep sea mining operation globally. The aim is to mine deep sea hydrothermal vents at depths of 1,600 meters inside the New Guinean EEZ. So this is an incipient industry. It's not just confined to hydrothermal vents potentially, but there are also mineral deposits on seamounts called cobalt crusts or iron manganese crusts. There are marine phosphate deposits which tend to occur in areas of high productivity in the ocean, and there are manganese nodules lying on the abyssal plains which are also subject to a great deal of interest in terms of commercial exploitation. There are various estimates of how much these mineral reserves may be worth, but really I take these with a pinch of salt, because almost on a monthly basis new types of deposit are being discovered, and of course the entire economic situation globally is going to have a bearing on whether or not these deposits are actually exploited. Of course, these types of operations have serious potential consequences on the deep ocean. We simply don't really know yet, because this type of activity has not taken place, so we're keeping an eye on the Papua New Guinea situation very closely. But one of the important things about deep sea hydrothermal vents is they have highly endemic communities of animals. Those communities are simply not found elsewhere in the deep ocean. So these ecosystems were discovered with the publication of a paper in 1977, so they're relatively recently discovered. And what you see here are what we found in different parts of the global ocean. So in the eastern Pacific, where these ecosystems were first found, you see these giant tube worms, these types of crabs, these hydrothermal vent mussels. In the western Pacific, we also see tube worms, but also snails, barnacles, and so on. In the Atlantic, the vents are completely dominated by swarms of these shrimps, but also, again, the hydrothermal vent mussels turn up. The Indian Ocean, strangely, looks like a mix of the Atlantic Ocean fauna and the Pacific Ocean fauna, with the odd local speciality. And this is the scaly-foot snail, which is the only animal that secretes iron armour. These scales on the feet are made of iron, and we think they're there to protect the animal against predation and probably the environment to some extent as well. You'll notice just how rich these ecosystems are compared to that picture I showed you of the flat sediments covering most of the ocean. And the reason for that is that the entire ecosystem here is based on chemosynthetic production. In other words, bacteria around these hydrothermal vents actually use chemicals like hydrogen sulfide, which they oxidize to produce energy. So chemicals replace sunlight in these ecosystems, and so we see almost an endless production of food around these vents. And many of these animals, for example these tube worms, they don't have a mouth, they don't have a gut. What they have is symbiotic bacteria living in their tissues, which the animals provide with hydrogen sulfide and oxygen and so on, and the bacteria provide the animals with nutrients. So we got very interested in why we saw these relationships between different parts of the world ocean, and the obvious pathway between these oceans was the Southern Ocean. Now, nobody had gone to investigate deep sea vents in the Southern Ocean simply because it's such a horrible place to work. So we decided to go there in true scientific fashion, and we knew that there was some hydrothermal plumes, the chemical signature of vents, on a structure called the East Scotia Ridge. So you can see here, this is South Georgia, here's the Falkland Islands, this is the Antarctic Peninsula, the South Sandwich Islands, and here is the ridge. And we found hydrothermal vents in two places on that ridge. One was an area called the Mermaid's Purse in the north of the ridge, and you can see why it looks like a dogfish egg case. And what that is a swelling of the ridge where there's a magma chamber underneath. And the other place was down south, actually in true polar waters, which were in fractures lying adjacent to this collapsed crater in the ridge. This is probably about 2 miles across and several hundred meters deep, this structure. It's absolutely huge. And we also found an entire new volcanic crater, which you can see here next to the South Sandwich Islands, and that too housed hydrothermal vents, but of a very different nature. So we visited this area in 2010, and this is what we found. And this was a site at the time which had never been seen anywhere else on hydrothermal vents globally. These are called yeti crabs, and the reason is, if you look at them, you'll see that they are hairy underneath. And what they do is they grow bacteria on the hairs and just comb them off and eat them. And as you'll see, when I say that the production in these systems is high, it really is quite amazing. I cannot tell you how excited we were when we found this with the remotely operated vehicle we were looking with. One of my students nicknamed these animals the Hoff crab, after David Hasselhoff, who has a notoriously hairy chest. That immediately went viral around the globe, so these are very famous crabs. We also found these large snails. These have symbiotic bacteria in a gland in the foot. That was a new genus and species. And indeed, every single large animal we found in these vents was new to science. Something like 24 large animals. The fascinating thing was that we didn't find many of the things that we thought we'd find. So there were no tube worms, no shrimps, no mussels, and various other groups were actually missing from these subnocean vents. And it seems that the Antarctic polar frontal zone actually acts as a barrier to dispersal for many of these groups. And we think that's got something to do with their life history and the fact that they just cannot survive in polar waters. And it's interesting to think that this one single cruise that lasted about 5 weeks actually completely changed our idea of the distribution of fauna around these hydrothermal vents globally. So this is a model of different types of communities on hydrothermal vents, and the different coloured symbols represent different types, and we estimated there are about 11 different types of community on these vents globally. So this brings us back to the Indian Ocean and marine mining, and what you see here are essentially mining concessions or concessions for exploration for mining on the southwest Indian Ridge, the area where we were working previously, and also the central Indian Ridge as well. This is a Chinese license area for deep sea mining in the area. And these licenses are basically given by the International Seabed Authority, which is a UN body based in Jamaica. So they're charged with actually licensing and managing this type of activity in the high seas or the area. These are concessions licensed for deep sea hydrothermal vent deposits, and here you see a different concession. This is by India for manganese nodules in the deep abyssal plains. We happened to visit the hydrothermal vents, which are now subject to exploration by the Chinese for mining, and this is what we found. And interestingly, we came upon some familiar friends along this ridge. It'll take us a couple of seconds to get to the beast. This is a beehive smoker, which is named for obvious reasons. And here you'll see the vent shrimps that are very, very similar to the ones in the Atlantic. Really quite amazing, delicate structures for some of these black smoker chimneys. And here we see stalked barnacles and lots of these snails, some of which are the scaly-foot snails, but some of which turn out to be a very close relative to the snails that we found in Antarctica. And indeed, just wait a minute, lo and behold, also on these vents turned up these yeti crabs. Again, very closely related to our Antarctic species, but probably a separate species. And it looks like some of the elements of the Antarctic fauna is using the ridge system to basically move from one part of the ocean to another in this case. So these are horrible spidery genetics diagrams that we build. You can imagine them essentially as family trees with different species and groups of organisms at the tips of the trees. And here are our two snail species, one from Antarctica and one from the southwest Indian Ridge. And again, the yeti crabs are portrayed here. So they're very, very closely related. And that separation has occurred relatively recently. Last year in February, I was really, really lucky to be able to join JAMSTEC on one of their cruises to the central Indian Ridge, where we dived in this submersible, the Shinkai 6500. And here you can see me peering out of a porthole about 2 miles down on the central Indian Ridge. And you can see this really does look like space exploration. We're not wearing astronaut suits because, quite frankly, if any of this failed, we'd be squashed flat very, very quickly. So there's not much point in wearing anything like that. But these are the vents on the central Indian Ridge, so in the same ocean and connected with those on the southwest Indian Ridge. And indeed we see the vent shrimps and the mussels that we see on the southwest Indian Ridge, but what we don't see here are the yeti crabs or the other types of vent snails. And also we've looked at the genetics of the scaly-foot snails. This is another vent system along the same ridge, but deeper this time, 3,000 meters. Looks very, very similar to the previous one. But when we actually look at the genetics of populations of these scaly-foot snails between the southwest Indian Ridge and the central Indian Ridge, what we find is that there is a big genetic discontinuity between those two ridge systems. In other words, larvae are not travelling between these two systems, and that means that if we destroy one of these vents, then there may not be recolonisation of that vent from another area, so it can recover from that exploitation. So this is quite important research in trying to understand the connectivity between these different ridge systems. So moving on now to Nekton, we're very interested in basically the deep ocean and the protection of deep ocean biodiversity and looking at human impacts. And this is a really hot topic at the moment at the UN, because there is negotiations going on at the moment over a new implementing agreement for the UN Convention on Law of the Sea to do with biodiversity beyond national jurisdiction. In other words, we're looking at establishing a legal framework for protection of biodiversity in the deep sea, rules for environmental impact assessments, and rules around the use of marine biotechnology from this zone. And in Nekton, we're particularly interested in two zones of the ocean. The first one is what we call the mesophotic zone, and this is particularly important in areas where you get coral reefs, because it turns out that below the normal depth that scuba divers go to, there's a whole depth zone in which light-using corals actually exist, which is almost unexplored. And the reason it's kind of been missed is it falls between the depth at which conventional scuba diving takes place and the use of deep submergence gear, such as submersibles and ROVs. So we're very, very interested in this area. And we're very interested in the bathyal zone, the zone from 200 to 2,000 to 3,000 meters, because it's in this area that we get the peak in biodiversity in these deep sea communities, and also many of these hotspot ecosystems in the deep sea as well. And scientists have done some work where they've divided the bathyal zone into 14 different parts of the globe, and this has been done just on looking at how environmental conditions differ between different parts of the ocean. And our intention is to explore representative ecosystems from all of these different 14 biogeographic zones. Core to Nekton's mission is really to develop standardized repeatable protocols that are not just used by us, but other scientists working in the deep sea as well. Looking at technologies to accelerate the production of science and the movement of science to policy or policy relevant information. Big data, we have something called the Ocean Tool for Public Understanding and Science being developed really to allow people to access marine data in a very easy way. New technologies, capacity building, to actually work directly with policy makers, and also to have a strong element of education and public outreach. And the first mission for Nekton, which is the XL Kaplan Deep Ocean Survey, took place last year in Bermuda. Now, you might think this is a strange choice of somewhere to go, because there is a marine station on Bermuda. There's been lots of work done around this area, and we weren't expecting to find a huge amount of new stuff. So the technologies we used were submersibles. This is a Triton submersible, and you can see here this submersible doing a survey transect along the seabed. It's got stereo video cameras pointing forwards to look at fish communities and a camera pointing downwards to look at the seabed communities. Here we can see some technical divers doing exactly the same type of survey work, except they were working down to 90 metres and the submersible's down to 300. An average dive for these guys was about 7 hours long. Okay, they dived in teams of 3, and I must say, as a scuba diver, I was really impressed. And this is the type of thing we found. This was totally unknown in Bermuda. It's a forest of black corals. They're twisted wire corals, and you can see the submersible moving through it here. Really quite a spectacular system. And what we also subsequently discovered, part of the way that we work is we have a rapid taxonomic identification workshop after the expedition. So this chap, Daniel Wagner here, is an expert on black corals. He discovered 8 species of black corals from our samples, 3 of which were new records for Bermuda associated with these deep coral forests, 1 of which may be a new species. And this is in a part of the world which has been relatively well worked up. And you can see here, these were the most common habitat forming group in waters deeper than 100 metres, and they're often associated with other animals. Here's one of the submersibles on top of a seamount, the Argus Bank. This is at about 70 metres deep, and you can see it's completely covered in this deep algal bed. This is an alga called Spiropnus. I just love the way that these fish kind of disappear and reappear from this mat of green. It's really quite spectacular. But Craig Schneider and Thea Popolizio, who've been working on the algal collections from this expedition, have discovered a wealth of new species. So we see here, this is one of them, Cryptonemia abyssalis. Here are 2 more, Galeni spur, Saramenia septentrionalis, and here we've got even more, and their work is still in the early stages. So why are they finding all these species? Well, simple thing is that these algae do not occur in shallow water because they're all grazing animals living there, like parrotfish and so on, which simply graze these to nothing in shallow water. So now that we've got samples from deeper water, we're sampling a very different community of algae. And this is the global distribution of Saramenia, and you can see that there are 4 species that have popped up in quite disparate parts of the world. What this suggests to me is we're only just touching the tip of the iceberg here in terms of what's known about the deep ocean. You'll see here the Indian Ocean is a complete blank. Nick Scheizas from the University of Puerto Rico has been looking at the small animals associated with things like corals and sponges, and this kind of microcosmos of creatures is turning up again an abundance of new species. You see here these tiny crustaceans, that's a scale bar for 1 millimetre, 12 new species of Tanaids, new species of leptostracans, new species of various other things. This is a sea spider. And there are new records of bigger things. It's not just invertebrates. And I must just read you this excerpt from a piece that was written by a writer called China Meeville, actually, who participated in this dive. So, from beyond a rock, a sine curve comes, a predatory cloth strip. The moray swims without speed, assiduous undulations, bile-coloured, calm, hateless it looks. Hateless it looks like, and untroubled by the cut of your light through which it passes on its side, bringing its rippling shadow close. It comes near enough that you can see its full stop eye, and if that's not eel curiosity, it looks like it. So again, this is an example of the outreach work that Nekton did with this expedition. We had writers and artists involved in working on material after the cruise and participating in the cruise as well. Whoops. Let me just here again is another new record, which is this fish. This is Darwin's slimehead, not the most attractive of names, but a new record for Bermuda. But what I point out here as well is this critter sitting on the seabed there. This is several hundred metres deep, and what you see there is an invasive lionfish. And actually what we discovered during this trip were the deepest occurrences of lionfish in the Caribbean. These animals have now invaded down to depths of more than 300 metres, well through the mesophotic coral ecosystems and now into the upper bathyal zone of the Caribbean. This paper is actually available on the web now and will be through the peer review process fully shortly. I'm just going to briefly mention the education and outreach as well, because there are people who are far more expert in this than me in the room. But just to say that the outreach activities in Nekton reach 750 million people globally. And this is outreach the like of which I've never ever seen in a scientific project related to the ocean. James is here, who worked on the STEM education programme with Digital Explorer. And you can see also, as I said, we've had various art events. We had release of a World Heritage report on World Heritage sites in the high seas during the report, and various other publicity articles as well. So just to summarise all that, we're still in the exploratory phase of deep sea biology. Human exploitation and pollution have already impacted and contaminated even the most remote parts of the deep ocean. We discovered the first vent fields in the Antarctic, which changed the view of global vent biogeography. We've seen evidence of faunal connections from the Antarctic to the southern Indian Ocean. This is simply the largest ecosystem on Earth. It's a global commons and poorly protected, and really knowledge is the key to sustainable management of this ecosystem in terms of human activities. And finally, I'd just like to thank all of the people who funded and supported us as partners for the Excel Catlin Deep Ocean Survey, and who are working with us subsequently as well. And also, of course, IMarEST for allowing me to come along and give this lecture tonight. So, thank you. Questions? Yeah, very happy. Yeah.
May I ask a little bit about the seabed current, not the sea surface current, but the
deep currents.
Deep current. How is it affecting the observation of ecosystem?
Well, deep currents are very important in terms of connectivity of different parts of the ocean. So many marine animals disperse as larvae in the water column. So they release eggs into the water overlying the seabed, and then they're transported on currents from one place to another. So currents are immensely important in terms of connectivity of different communities across different parts of the ocean, and that's over a wide range of temporal scales. So you know, going through to patterns of speciation that we see in things like the vent communities, to actually contemporary connectivity between systems. One thing I would say is that one of our recent discoveries is that the deep ocean is absorbing a huge amount of heat at the moment that is resulting from CO2 emissions. So of course there are concerns that that will alter temperatures of the deep ocean, and also alter basically the distribution of water masses and alter ocean currents and so on.
Water at the almost seabed is also moving.
Yes.
Different from the surface.
Yeah, yeah. So immediately local to the vent, the heat causes the water to be buoyant. So that's how we detect where these vents are. They have buoyant plumes which go up several hundred meters into the water column, and we can tow instruments with sensors that pick up those plumes along the seabed. And then of course you have the wider ocean currents which flow over the ridge systems and along them in some cases. And those can be important in terms of dispersal and connectivity of one vent to another.
Even without the vent system.
Yes, there are still currents there. In fact, that Antarctic cruise, we had a whole 5 or 6 weeks trying to find those vents, and one of the problems we had were there were tidal currents at 2,000 to 2,500 meters that were blowing the plumes around. So we drop our sensors down, we detect the plume, get very excited because we thought we'd found where the vent was. Then the next time we dropped it down, it disappeared. And what was happening were the currents were changing on a daily basis and just moving that plume around in the water column. Yep.
Obviously from the missions we saw that there's a huge amount of life down in these areas. I was wondering, you talked about the exploration companies and governments researching actually the deep sea mining stuff. I was wondering if you or any other companies are actually going to be working with these people to find out what the effects are going to be on the environment.
Yeah, there are several scientific programs at the moment, some in the UK and some elsewhere, working on various types of mineral deposit. So there's a big program at the moment in the Clarion-Clipperton fracture zone in the Pacific, looking at distribution of animals across that area, which has got a vast series of mining concessions associated with it, or exploratory licenses associated with it. Some of those groups doing that work have been working with some of the companies that potentially will be going in there, people like Lockheed, for example, and so on. Other governments tend to have government research programs, so China, for example, South Korea, India, and so on. They're tending to work through government research institutes, looking at the environment around those sites. Yep.
As well as hydrothermal vacuum synthetic environments, are you going to be looking at coal seeps too?
If we find them, yeah. The whole question of chemosynthesis is really interesting at the moment. After vents were found, as you probably know, hydrocarbon seeps were found. So these are places where methane and other hydrocarbons come out the seabed and again act as chemical fuel for life. But we're also now discovering, not me personally, but other people who are working on this thing, that chemosynthesis is going on right through the water column. And we're not quite sure how, because it needs an anoxic environment, that particular type. And what we think is going on is that there are microenvironments on the marine snow and particles sinking out from the surface that are oxygen free, and that's where this activity is going on. So there's a whole question there of just how much primary chemosynthetic primary production is going on in parts of the ocean where, you know, we had no clue 5 years ago that this was happening.
I have a question myself, not online, although people have been watching, which is great. Obviously we can see there's going to be a big push to explore the deep sea for mining from the commercial side. Is there an opportunity to piggyback scientific knowledge off of the deep sea mining? Kind of akin to the way that archaeologists are allowed to explore a building site for a period of time before they then go in and build the building. Can you learn from initial exploration?
Yeah.
How would we achieve that?
I think some of that is happening. As I said, scientists have been working out in the Pacific, and I think there certainly has been trials now going on for several decades on sort of doing artificial disturbance experiments and looking at recovery times and so on. And there's been a new wave of that with a renewed interest in deep sea mining. However, I must say that in some other instances, governments who have the licenses have been very discouraging of people going into the areas where they have licenses. Now, I personally experienced that in February. I don't want to cause a diplomatic incident by saying what happened, but I can tell you probably afterwards. But certainly there's, I think there's the potential for significant damage to be done through some of these exploratory activities, and there's no way, unless we get large ships out there and the right equipment down to look, to really document what is actually going on.
So unless if the licensing stipulates that they have to go in and do the surveys and the sampling,
Yeah.
but without that, then
I would be concerned about the independence of those types of operations. So, yeah.
Specific question on part of the ecosystem, because many years ago I went down on the Cayman Walk to 1,000 feet and was struck by what they describe as the sponge belt, with huge sponges looking like Salvador Dali paintings.
Yeah.
And I just wondered if you comment on that, the sponges.
Yeah, and in fact, we see similar sponge belts on the continental slope off the UK. And in fact, there's been a big DEFRA project, not DEFRA, CFAS project recently looking at those where they occur and using modelling again to predict where they occur and where they may have occurred prior to fishing taking
So this
place.
could be a worldwide phenomenon at certain depths.
I think certainly, I mean, it looks like it's a more common phenomena than we may have realised 10, 20 years ago. We were aware for probably since the 1950s or even earlier that there were certain parts of the northeast Atlantic where we see what are called oster, which is a Norwegian or Faroese word, which actually means cheese bottom. Does conjure up a picture of this. But what that refers to is the fact that when these sponges come up in a trawl, they look like cheeses, basically. And of course, those sponges are associated with a high diversity of other species. And in fact, one of the areas we've been looking at with the Northwest Atlantic work is the influence of the presence of sponges on the diversity of animals in
Because they seem to function almost like a coral reef with animals living in it.
That's absolutely right. And in fact, there are literally sponge reefs, and they've certainly been found off the west coast of Canada in depths of a couple of 100 metres there, because they're a very special biogeographical conditions. But elsewhere, you get these dense gardens of sponges. And I suspect that, as you say, they're probably much more widespread than we've originally thought, as I suspect those deep wire coral habitats. I suspect, and because I've of course seen this in Bermuda, I'm now starting to look for the same habitat in photographs from elsewhere. And, a similar sort of habitat seems to occur here or there. So it may be that that type of habitat is also more widespread. The interesting thing is that all of these seem to occur in that depth zone between 200 to 1500 metres. And I think that has something to do with, well, first of all, food supply, but also active transport of carbon from the surface to the seabed. So we have these layers of migrating plankton which come up to the surface at night and feed and then dive down into the deep to avoid predation during the day. They act as an active mechanism for transporting organic material from the surface to the deep. And that migration certainly occurs over that depth zone. We're also seeing things like internal wave formation and internal tides which can transport primary production direct from the surface down to the deeper seabed in some of those localities. So those areas seem to be, in terms of currents and so on, very energetic, and that's why the sponges and the corals are there.
Yes, I was intrigued to hear you talk about the orange roughy. I'm from New Zealand, and I was involved with shipping of that of container loads, and of course it declined. The species declined. Now, I'm not sure where they are at the moment, but and your comment about your vents, underwater vents, that's a big subject at home at the moment, because they're not sure what they're going to do.
Yeah.
But on the west coast of New Zealand, there's intensive iron sands being exported, and it's large, very large.
So is that coming from the shelf or from deeper water?
It's it's the north, the west coast of the
jump into that. Interestingly, New Zealand recently made a decision to turn down a license for phosphate mining in deep water habitats because they happen to coincide with some of their deep water marine protected areas.
Yes.
And that's the first time that a decision like that has been made globally. But another interesting adjunct to the orange roughy story is when they were first caught, they couldn't sell them. And so they were literally bulldozing them into landfill. And what happened is the marketeers then thought about how to sell them, invented this name of orange roughy rather than slime head. And then once the market had taken off, they went in and fished them, and you've got this situation of serial depletion where they'll fish them out from one area and then move on to another, and so on. The only area where it seems to have been sustainable to some degree, and I'd have to look in more detail as to what's going on now, is the Chatham Rise.
Yes, it is the yes.
Yeah, because I think that area is getting a lot of nutrients from land, essentially.
Yes.
So it's an unusual area.
So there's a big, well, I think it's 200 miles we're trying to keep safer or under our control.
Yeah.
Thanks very much.
Yeah, cheers.
Okay, well, I think from the number of questions, which is unusually high, it's fantastic, shows how interesting tonight's lecture was, and I think we shall thank the professor.